You'll just have to learn in lab. All right, so the fission reaction here, it's the nuclear chain reaction. That's what we're writing, nuclear chain reaction. So this keeps reacting and reacting and reacting until all the fuel is gone, all the uranium's gone. The nuclear fission reaction cannot stop until all fuel is depleted. So once the people in the nuclear power plants, and there's a lot of machines involved and robots because they can be down in the radiation and humans can't. When I say robot, I'm not talking about like, walking, talking robots. I'm talking about just machines that we control. When they're operating the reactor core, once this starts, we cannot stop it. So there's no like off button. Like you can turn your car off, it stops. It's dangerous for this reason. Nuclear reactions will continue and humans can't stop it. So once we start this fission reaction, it cannot stop until all of the uranium has been depleted. Now, we sort of can stop it because these fuel rods, they're kind of like meters thick. I think they're about 1 meter long. And they're very thin, kind of like maybe a little thicker than this. Never seen one in real life, but the fuel rods get put down like into the core, so I suppose we can pull the fuel rods out. And the neutrons are in here bouncing around. If you take the fuel rod out, then the reaction can stop. But I guess what I'm saying is once it's going and the fuel rods are in the core, it's going to keep going. We can't just interrupt the reaction. So we have to keep it controlled or it can melt down. That's a big negative of nuclear power plants, I would say. So that's important. So what are we learning here? What's fission? It's called a nuclear chain reaction. I'm going to show you a video that really shows that well. And then once it starts, we cannot really stop it. Okay. So the other reaction, I'll just give it to you quickly here, is when plutonium goes through it. All right, so plutonium, I mean it's 239. Plutonium 239, 94, plus 1 neutron. So that's why it's artificial transmutation. We're slamming that with a neutron. We get barium and strontium, and we get 13 neutrons this time with a lot of energy. So it's like super exothermic. Okay. All right, one more thing I want to talk about fission here, and then I will show you a video on fission, and then we'll talk about fusion, and then that's probably going to be it. And we do have a worksheet for homework. Oh, there is a back. Good for me. I don't want you guys to be too bored. You had a long bus ride.
Yeah, it's
Do it on the bus.
no, it's sick.
All right, so let's do tomorrow. Okay, eyes up here. What's the mass on the left side? 240. So the mass here, write this down, 240. What's the mass on the right side? 240, very good. Mass is 240. And we'll just say grams, but it's really atomic mass units, but that's fine. Okay. That shows the law of conservation of mass. So on that homework that you showed me today, Nicole, and everyone else the other day, that homework with the fill in the blank, you're supposed to balance the numbers. So the numbers on the left and the numbers on the right are equal to each other. Well, on paper that's great, but in real life it doesn't work that way. So in real life, so this is like on paper, okay, write this down. Real life, let's say we start with 240, but we end up with 200. So we are breaking the law of conservation of mass. In real life, the mass of the products in all nuclear reactions I'm using fission as an example. But all nuclear reactions, the mass of the products always less than the mass of the reactants. Where did it go? Energy. Mass is converted to energy. You know who figured that out? Not that long ago. Really smart dude. Manhattan Project, the atomic bomb. He was in charge of that project. White hair, mustache.
Albert
Einstein. He figured out that you can convert mass to energy in a fairly famous equation. E
was MC squared.
equals mc squared, right? So E is energy, m is mass, c is the speed of light. There's a lot more to it, but so this is to you sitting in chemistry class on a Tuesday, random Tuesday here. This is not like super interesting or exciting. Maybe it is. I mean, I think it's cool. I'm interested. I like it, but you're a little bit removed. It's kind of a big deal to take the nucleus of something and then turn that into energy is a big deal because the forces holding the nucleus together are really, really strong. So when you lose the mass and it's converted to energy, that's a massive and incredible amount of energy. An incredible amount of energy. So write this down, please. Mass is converted to energy. That's why nuclear power is so powerful and so dangerous. Not just because of the radiation, but because the sheer amount of power and energy. Sorry, I wrote on the line. That's kind of there. Let me give you an example. Do you guys know how many pounds are in a kilogram?
I don't know.
Isn't there 1,000?
That's 1,000 grams in a kilogram. It's about 2.2. So, 2.2 pounds in a kilogram. So if you have 2.2 pounds of uranium, okay, write that down. That's equal to, so the amount of energy 2.2 pounds of uranium can produce through a fission reaction, let's say, or a nuclear reaction. Stay with me. 2.2 pounds of uranium is equivalent to $40 million pounds of dynamite. So 2.2 pounds you can hold in your hand. That's very light. You can't hold 40 million pounds. So when you take a stick of dynamite, light it up, and it blows up, a stick of dynamite, I don't know, let's say it's half a pound. Okay? 40 million pounds of dynamite, that explosive power is equivalent to 2.2 pounds of uranium. That's incredible. That's incredible. All right? That's an insane amount of dynamite. All right? That'd fill up literally the entire school, more than that. So just a little tiny bit of uranium gives off the same amount of energy as that. This is why it is so dangerous and so powerful. But if you can harness this carefully and successfully, you can get a lot of electricity from it. So nuclear power plants, that's what they do. They take the energy from the fission reaction and they turn it into electricity. So this is kind of staggering. It's like almost big enough where we can't even really comprehend it. That's a lot of energy. So that's why the atomic bomb levels entire cities. All right, the radiation on top of it makes it even worse. So that was kind of the last thing I wanted to mention there with the power of the fission reaction. Let me show you the video, and then we'll move on here. Oh boy. Hey, I guessed right. There it is. Okay. All right. So, there you go. Glad
Nuclear fission is the splitting of a heavy element's nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces U-236, which immediately splits into two lighter elements, such as krypton-91 and barium-142. The fission event also releases 3 neutrons and energy. The 3 neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of a massive amounts of energy in the form of heat, light, and ionizing radiation.
Okay, it's a great video because that's what the chain reaction is. So they just keep colliding and colliding until they run out of uranium to collide into. That's the chain reaction. All right. That's why it's so powerful, because it just keeps increasing and increasing and increasing. More and more neutrons being produced. So in a nuclear power plant, that energy is used to create electricity. Do you know how they do that? Did I tell you guys yet? It's very simple. They just boil water. So they take all that energy and boil water. Nuclear power plants boil water. That's it. What do they do with the boiling water? They capture the steam. The steam turns turbines. You guys know what turbines are? Maybe. Turbines create electricity. When you spin a turbine very quickly, it creates charge. Kind of like if you rub your feet on the floor and then touch something metal, you get a shock. Same concept. It rotates so fast and produces electricity, charges. And steam does that. So this energy is used to just heat up water, which produces steam when it boils, which turns turbines. That's how nuclear power plants work. A lot of people think it's not worth it because what's a byproduct of these reactions? That would be harmful to us. Radiation. There's radioactive waste that we have to store for like thousands of years. Stay radioactive, half-life, thousands of years. So we'll talk more about fusion tomorrow. Good luck on the homework. One of them I didn't talk about yet. Not really.